This is Conceptual Physics, review day 2. We're going to review everything we learned about Newton and his laws. So remember, there are 3 laws that Newton came up with. His first law was the law of inertia, which says that you need an unbalanced force to change the motion. So that means that you have to push, you can have more than one force on it, right? And balance out the forces so that pushing left is equal to pushing right, and then it doesn't have a net force. But as long as it has a net force, so one force is pushing more than the other one in the other direction, you're going to change your motion. Changing motion means you can go faster, you can go slower. You could start, you could stop, you could turn. There's all sorts of things as long as you change your motion, right? But you can be going at constant speed, and then you don't have to have an unbalanced force. You just keep going. So when you take the forces all away, it still moves. That's the hardest concept. Remember, inertia means a resistance to a change in motion. So the object doesn't want to move unless there's that unbalanced force on it. For the second law, we know that F net is equal to ma. That means that force and acceleration are directly proportional, and mass and acceleration are inversely proportional. So that means that if my force goes up, my acceleration goes up, right? And if my mass goes up, my acceleration goes down, right? So that makes sense, right? A big boulder is not going to accelerate for the same force, that type of thing, at the same rate. Third law is action-reaction. That's the idea that 2 objects push on each other with the same force. And they're always trying to ask you questions to get you to say, oh, the bigger object has more force. Like the big truck runs into the little car. Which one has more force on it? Well, they're the same because they run into each other. The sun pulls on the earth and the earth pulls on the sun. Which one pulls harder? They're the same. It doesn't matter that the sun is really, really big. I push on you, you push on me. It's the same because of Newton's third law, action-reaction. Main concepts. A moving object does not need a force, right? That's what we said. So if I throw an object out in space and there's no forces on it, it will keep going forever. If I roll a bowling ball down the alley, it should keep going because there's basically no friction on it, right? It's a misconception that things stop because of there's no force on it, right? You need a force to keep it moving. So you need to remember that when something has its force removed, it keeps moving. It doesn't need a force. And then the net force is the sum of all the forces. So you set the sum equal to ma, not the applied force. Example, here's a box, right? And let's say I push with 20 newtons this way, and then somebody else pushes with 5 newtons this way, but then we've got maybe friction that's pushing back with 10 newtons. So that would mean F net is going to be equal to 20 plus 5 minus 10 newtons. So 20 minus 10 is 10 plus 5. So that would be 15 newtons is my net force. And that's what I would set equal to MA, not the 20 newtons that maybe I'm pushing with or the 25 newtons that me and my friend are pushing with. Bigger objects do not apply more force than smaller objects, right? I don't care how big the fly hits the windshield, it's the same force. I don't care how small the fly is. You got to get that into your head. Then we talked about types of forces. So there's something called gravity, which we call weight, which is your downward force. So we normally, it's equal to mg always, but we also call it Fg. That's what we call it lots of times. The normal force is perpendicular to the surface, and so that's equal to Fn. And then you have friction force, which we usually call Ff. And the force of friction is equal to mu. Remember that funny looking thing? So Ff is equal to mu. I don't like that. Let me fix that. Hang on. Let's make it look better. So the Ff, the force of friction, is equal to that funny mu times n. And tension is the reaction force by the rope. So if the rope is hanging, then the tension is just equal to weight divided by the ropes. So let's do a couple examples real quick here. So let's say that I have an object and it's sitting on the ground and I'm pushing it with 5 newtons. What other forces are acting on it? Well, I know gravity is going to act down, and I know normal force is going to act up, and I know my friction force is acting to the side. And so maybe I want to figure out which ones are equal. Well, I know Fn has to be equal to Fg because it's not going in that direction. And then since it's moving the other direction, I don't know about if at constant velocity, then I know 5 is equal to F, right? But it's only if and only if it's moving at a constant velocity. And then when we're looking at the tension force, right, if we want to look at an example of the tension force, if I have an object that's hanging by some ropes, let's make it 3 ropes, and let's make it 300 newtons, then we know we have 3 tensions, tension 1, tension 2, tension 3. Since they're all pulling directly up, then that just means that T1 plus T2 plus T3 has to equal 300. So therefore, by logic, we can say, oh, it's divided up 3 ways. So that must mean that all the T's are equal, and they must all equal 100 newtons, right? So that's the kind of logic you need to use when doing those type of problems. Here's some sample problems that we can do in 5 steps. A 5-kilogram box is pushed with 50 newtons. And the floor provides 2 newtons of friction. What is the acceleration of the box? So, of course, we're going to draw a free body diagram. It's sitting on the floor, and it tells us that it's a 5-kilogram box. So that means 5 kilograms. That means Fg equals 5 times 10, so it equals 50 newtons, right? And so it also says it's being pushed with 50 newtons, okay? And then we have normal force going up, but since it's not moving up and down, we know that this must be equal to 50 newtons because this and this, Fn and Fg, have to be equal because it's not moving in that direction. Now, it didn't say anything about constant velocity. Matter of fact, it even says acceleration of the box. So we have this other force, which is force of friction, but it tells me that it's 2 newtons, right? So I don't have much space there, so I'm going to do this problem right here. So in my given, I have M equals 5 kilograms, and what is my F net? Well, I look at the picture and I go, oh, well, it's got to be 50 minus 2, right? So, okay, so F net is equal to 48 newtons, and I'm trying to find the acceleration. So I know I had all this other information, and I could have put everything in there, but I just wanted to have the things I needed, so I could have had the other things there as well. My equation, of course, is Newton's second law, which says F equals ma, but now I need to solve it for a, so I divide both sides by m. Smooth this up just a little bit, so a little more space. And so that means for my solve step, we cross off the m's, so a is equal to F over m, and then if we compute, see, A is equal to, what was F? F was 48. 48 newtons divided by 5 kilograms. So I pull out my handy-dandy calculator, and I do 48, and I divide it by 5, and I get 9.6 meters per second squared. Right, in the same direction as the force. All right, so that was B. Let's try let's try B. It says a 500 kilogram sign is hanging from 4 similar ropes. What is the tension in each one of the ropes? Well, I don't need to do that in 5 steps. I know there's 4 ropes, so I say, oh, I know what I'm going to do. I know that T is going to be equal to the entire, now, is it 500 kilograms? No, I got to change it to newtons, so I know that's 5,000 newtons because I multiplied by 10, so 5,000 newtons divided by 4. So I pull out my calculator and I do 5,000, and I divide it by 4, and I get 1,250 newtons in each rope. Yeah? Okay. Engineering task for this one. The engineering task for this one was an accelerating aircraft. So we used a ramp and a pulley system to accelerate the aircraft with gravity. So remember, we had this We had the motion sensor, and we had the ramp, we had a little pulley system, we put the car here, and then we put the masses here, and so this FG was causing it to accelerate. So that's what we mean by we accelerated the aircraft with gravity. We used that to pull it down and pulled this forward like that. Remember, you needed the acceleration to be 1.6 meters per second squared, so you did a graph of F versus M, and you got a line, and then the slope was the acceleration, which you were trying to set to 1.6 meters per second squared. And then I finally gave you an unknown mass, right? It was like a cup with a bunch of pennies that you stuck on your aircraft to make it accelerate, and you had to figure this out. So you came over here and said, oh, if I read here and read up and I read over, then that told me what force I had to do. But remember, this was in newtons, and so there was some confusion because you had to change it to grams. So you went, okay, so let's say I needed 3 newtons, then I knew I needed to have 0.3 kilograms, but then I had to move it 3 places, right? 1, 2, 3. So that meant I was like, oh, that's really tiny, 0.0003 grams. Well, hopefully you never needed that amount, because that would be way too tiny to be able to put on your mass hanger. But that is how you would do it if you needed 3 newtons.